Hello, in this video we are going to go over the solution of the problem of finding k closest points to the origin. So for example, I have the following points and each point has two variables. So the first one is the value of the x and the second one is the value of y. So x in x axis and y in the y axis, and I want to find the closest point to the origin. For example, this is 5, 1. This one is 2, 2, and when we go forward to see 1, 1 is the closest to the origin, and then we could probably say 1, 2, and then 2, 2. These three would be the three closest points to the origin. So we already saw a solution for another problem that was very similar. That was the problem of finding k largest elements in an array. So I'm going to use a pretty much similar code. So I highly recommend you to watch that video first, and then we go over this video. So after that one, then we showed a trick how we can use using a still min heap, but for finding k smallest. So we had another code that we showed how we can find k smallest elements in an array. So this time, instead of finding k smallest elements, first we make those points to the distance from the origin first, and then we calculate it. So for doing that, so I have the code here. So we want to find the k closest points. So the first thing that we do is that we are going to have a for loop here, and this for loop we are going to go over all of the points in our coordinates. So in coordinates we had all of those points 5, 1, 2, 2, 3, 4, and I go over them one by one, and then I calculate the distance of each point to the origin. So when I go, for example, CR0 here will be 5, CR1 is 1, so it's a 5 to the power of 2, 1 to the power of 2, SQRT of that, so that would be element here. So I put that in the first element of a new list that I'm appending to the list points. So I'm creating a new list of points, and that has three columns. So if I, for example, run this, so I can show you here what that looks like. So for example, that point that we just created is 5, 1. The distance is this one. So you can see I have three columns for the first point. For the second point, 2, 2, I have this one. For the third point, I have this one, and so on. So the first step is to creating that list that we have. So then it's pretty much similar to what we did in past for finding k, the smallest elements in an array. So that's the exact same code, just a small modification, and that is where we are using the heap. So if you remember, we had a variable k largest that was storing all of the nodes of the min heap. So here, when I'm going to use that k largest, so what I'm adding to the system is not only that points that is distance right now, so because it points the column 1 is the distance, I can also add the second and third columns of points to that. So let's see what happens if we do that. So when we do that, so what happens is this. So let me show you. So this is k largest. So for the first iteration, we added first three elements to the heap. So this is element 1, element 2, and element 3. By element, I mean the node that we added. So this is, but you see this k largest. If you notice that by default this should be the first always. Why? Because this has the lowest value, and k largest is the min heap. So it's always keep the minimum amount variable for us. So then we go over the loop again. So if I go for the loop again from n minus k, which is we start from k to, for n minus k iterations, which we start from k and we end to the n. So for that one, whenever I go forward, for example, for j here, let's see what happens. So we have, for example, j3. So the variable that I'm reading from the points is -2. This variable is larger than -5.0.09, so which was the other distance. So this compared to that, and oh, this is larger, so I'm going to replace that to the mean heap. So when I'm replacing that here, so not only I'm replacing that point, but I'm also replacing its coordinate here. So that is the exact same point. You see the j is similar with that point, so we are going to replace that one. For example, after one iteration here, so when I have this j3, so 2 was larger than 5. So what happened? Let's see what happened to my k largest. So k largest was -5, -2, -5. Now it is -5, -2.8, and -2.2. So you see this -2.2 here came here, and its corresponding coordinate system 1, 2 came here. So but again, if you look at this, the order that this shows you the elements is that this -5 will be the at the top of the mean heap, which is the minimum amount, because that is -5 is less than -2 and -2, and its corresponding coordinate systems are also there. So the main point is that this mean heap function that we have is the heap q functions that we are using for mean heap, and we are using these two functions, heap push and heap replace. So it will take care of all of the things that we want to do, but not only that, consider the first columns as your node, but you can add more columns to store extra information in your nodes. So for this problem, the first information in the column is the value of that node, that the minimum is always on top, but the second column and third column are going to be the coordinate system for us related to that point. So you can have more other information in different more columns here related that to node. So that is the point of this code, main point. So after the rest of them is just similar. So after doing that, if we finish this loop, all of the elements will be replaced that we need, and at the end we end up having these three coordinate systems that are the smallest one. So I just, for the last line, so you see we just that's gonna be iteration of k, so that we are going to just go over k largest and just return the x1, x2, which are the coordinate systems in k largest. So in that way, we should be able to solve this problem much faster than a naive to for loops and a for loop nested, which gives us the n squared. So let's look at the time complexity. So time complexity is again same as the previous problem that we have. The only difference is that here. So we have one more for loop here that we are going to go and visit all of the points that we were given at the beginning. So we have one extra n here. So I have an n, o n here, o k order of k here, and then here n minus k that we have, and we know that we have a heap replace here that is 2 log k here, and then we have a k here at the end to just show the results. So, and in case that n is greater than k, we can end up having order of n. So, and for space complexity, this time is larger because we are going to create a new variable called points and append to that all of the points to it. So in past we didn't need to do that, but here we are going to have that one. You might say, oh, okay, we have k largest, but k largest is always going to be k, and as we assume k is smaller than n, so the space complexity of this problem will be order of n. So that's pretty much the solution of this problem, and I highly recommend you to start from the first code, that was this one, k largest elements. So we saw in this code that how to solve the find the k largest elements just by first adding the first k elements to the mean heap and then going over the other elements one by one and save the time. And then we saw in the k smallest code how to use that -1 trick to be able to use mean heap when we need max heap. So that was the trick of the second problem. And the third problem, the only trick that we had was that when I'm adding the elements to the mean heap, so or max heap we call it. So for that one, when we are adding that to the heap, so not only I can add that value of the node that will be considered to decide which node goes on the top of the heap, I can also add more information to the list to that, and that could be very useful in a case that we need that later on. For example, for this problem, I don't care about what are the three closest distance. I care about what are the three closest coordinate systems. So at the end, I'm not returning, for example, minus 2.2 or something like that. What I want to return is that, for example, 3, 4, or for this problem, that was, I believe, that was 2, 2, 1, 1, 1, 2. I don't care about the distance of this, but I care about the location. So that's pretty much the solution of this problem. And again, thank you so much for watching this video.